Alright, let's do number 5 on the practice final. I'm worried that this one might be a little too hard, but it's just the practice final, so let's go through and do it. Maybe I can find a way to make this a little easier on the actual exam. So suppose a large wheel, radius 3. Okay, so in the picture here you can see that there's a big circle. That's the one that's going to be radius 3. So I'd rather that line be straight. So radius 3. It's not straight. Radius 3. Okay, and here's one of radius 2. And here's a little one of radius 1. And so what's happening here is the big wheel is turning the medium wheel, which is turning the small wheel. What we're given is the RPMs. So we're given the angular speed of the big wheel. Okay, so this 3 RPMs is the angular speed of the big wheel. Speed of the big one, big wheel. And what we want is to find the angular speed of the small wheel. Okay, so what we have to do here is use the relationship between angular speed, which remember is just radians per unit of time, and linear speed, which is, let's just call it r times omega. Okay, so really I think we can get by just with this if we're smart. So let's see. So the thing that makes this possible is that these wheels are spinning each other, right? So just think about the linear speed of a particle right here that's in this place where the wheels are touching. So the linear speed of all the wheels is the same. So I hope you understand what I mean. Like a little particle of sand coming in from this direction has a certain linear speed, that's arc length per second, and a little particle coming in from this direction has a certain angular speed, and they have to be the same because these wheels are flush with each other. Okay, all right. So let's just start with the fact that for this big wheel, omega is equal to 3. Okay, because it's 3 RPMs. Omega is just how many times you spin around a second. So omega for the big wheel is 3. So what is the linear speed for the big wheel, for something on the edge of the big wheel? Well, I use this formula. It's r times omega, so it's 3 times 3 is 9. Okay. All right, and so now let's look at the medium wheel. Okay. So we just argued that the linear speed on the perimeter of the big wheel is the same as the linear speed on the perimeter of the medium wheel. So that means here v is also equal to 9. Okay. Now, how many revolutions is it going to do per second? I need to use this formula again, right? So if this is true, it's really the same thing as saying that omega is equal to v over r, right? So if I want to figure out what omega is for this middle wheel, I can just use this. So omega is equal to the linear speed 9 over the r, which is 2, and so it is 4.5 RPMs. Okay, and the only thing that's left is this little wheel, and it's interpreting those things as straight. And so what's going on with this little wheel? Well, for the same reason that the linear speed of the medium wheel is the same as the linear speed of the big wheel, the linear speed of the little wheel is going to be the same as the linear speed of the big wheel because they're touching. They're touching right here. So particles on the surface of the two wheels must be moving at the same speed. And so use this formula again. Okay, so for the little wheel, the linear speed also is 9. Okay, so it's kind of weird. It's almost as if it were directly touching the big wheel. And so what else? So we have this formula for omega is the linear speed over the radius, but the radius of the small wheel is 1, so this is just 9 over 1 equals 9. Okay, and great. So we're done. This is the angular speed of the small wheel, and that's what the question was asking for. It says, what is the angular speed of the wheel of radius 1? And we just found it.